again, I will talk today about BrainScaleS via EBRAINS. And the subtitle is Easily Accessible Analog, because I guess most of you know that the BrainScaleS system is an analog system, and it tries to do brain emulation. And in the EBRAINS framework, I will go over details soon. It is planned to offer services for brain emulation to neuroscientists. And obviously, there are no experts. And therefore, it is important that we hide all the difficulties working with analog models from them. And this is why the subtitle here is Easily Accessible Analog. And let me summarize shortly the talk. First, I will give a background about our research group for the people new to NICE. And then I will also shortly introduce the Human Brain Project and EBRAINS, which is part of the Human Brain Project. After that, I will give an overview about the dimensions of neuromorphic computing, because neuromorphic computing is a vast field. We have heard yesterday in the opening statements different opinions, different hopes for the field. And we have already seen a lot of fantastic talks about the different dimensions of neuromorphic computing. And I will relate BrainScaleS to these dimensions and then show you what services we can offer with this kind of system in EBRAINS. And at the end, I will give an example, so to have at least some science in the talk about parameter fitting with BrainScaleS, which is important for brain emulation, and close with a summary. So our research group, it's the Electronic Visions group at the Kirchhoff Institute of Physics in Heidelberg. And I show this slide also to remind everybody of Karl-Heinz Meyer here. You see him here in the group picture below, the last group picture when he was still alive. Unfortunately, he died 2018, but he was one of the organizers of the NICE conference before, and we will always remember him. And he started his group 1995, and 2000, we built the first analog neuromorphic chips. And since then, they all have the same basic features. They're all analog, mostly analog. They have, use some digital electronics for communication. So it's kind of a mixed signal operation. And they all accelerated. So they all try to operate analog circuits, not in biological real time, but much faster. And the first brain emulation chip was the Spike chip in 2004, which used event-based or spike-based neuromorphic communication, and also included plasticity. And our first try to make neuromorphic computing accessible by having analog parameter storage that allows us to calibrate the analog or physical model, how we also call it, for a certain biological, to mimic a certain biological model. Now to the Human Brain Project, which is the main focus now of our research. It's it's a European project from the European Union. It's one of the so-called FET flagship projects. There are now other ones about quantum computing and graphene. And the first one, flagship project, was centered about computer science usage in neuroscience, called the Human Brain Project. Why was the focus on the brain? This is an old slide from the beginning of this project. It was about, I think, the same motivation a lot of people here in this community have: understanding the brain, understanding brain diseases. Okay, that maybe not that so much, but and developing future computing. This is so far, as far as I've seen the talks, this is the most, the most important aspect for most of the people here. And the developing future computing technology and also the brain emulation part for understanding the brain both lead to the neuromorphic section of the Human Brain Project. And in this section, there are neuromorphic machines, and one is Spinnaker. We will hear about this also, I think, today. And the other one is BrainScaleS from Heidelberg. And also there's a section about algorithms. I won't go into this today. And part of HPP is now this EBRAINS initiative. And the EBRAINS mission, they call it, these are original slides from HPP, not from myself, is enabling brain research advances and innovation. So you have the Human Brain Project. It is a big project running for 10 years, and it will now, it's now in the second last year, it will end next year. And in parallel, the project creates an infrastructure, and this it's kind of a European research infrastructure based on high performance computing and neuromorphic computing, which is located at several labs and high performance computing centers around Europe. And it's okay. I was talking about the EBRAINS mission, showing this original slide from EBRAINS. And the important thing here is that the results of the HPP is not only scientific results about how the brain works, but also a novel infrastructure for computerized medicine and computerized neuroscience. And this is called EBRAINS. And part of this infrastructure is the simulation of the brain-inspired technologies. And this is what is also covered by BrainScaleS in the EBRAINS framework. But this looks like it's a lot. EBRAINS is much larger, so the data and knowledge and the atlases are a much larger part. So BrainScaleS is only a very small part of EBRAINS. And it is part, you have seen, of the brain-inspired technologies, which is also known as brain-inspired computing. And this means that you all know this, that we want to compute more like the brain. And the methods are usually artificial neural networks, also called neuromorphic computing. You see such a sketch of such a network. I don't have to explain this to you. And to do this in EBRAINS, there will be novel technologies, novel digital and analog neuromorphic hardware, and also novel high-performance neurosimulations. Going back to the brain-inspired computing, there are two more or less different models used. We have heard examples from both in NICE so far. One is the perceptron model, you all know, which is more or less the core of the machine learning revolution. And this is also a very big part of the research in novel devices. We have seen a lot of this kind of vector matrix multiplication models, but not with digital electronics, but with analog electronics, or based on memristors, based on CMOS. Here's an example from our lab in 2001, where we built this kind of chip based on standard CMOS technology. And there's a different kind of brain-inspired computing, this using event-based or spike-based modeling, where we have a time-continuous dynamical system. We also heard at the very beginning of the conference in the opinions from the organizers that some think that this time-continuous dynamics is very important to understand the brain. And we have complex nonlinearities in the neurons. And this model allows to replicate biological local learning mechanisms in the synapses. So this is more or less the spectrum we have in brain-inspired computing or neuromorphic computing. And I try to summarize this in the so-called neuromorphic dimensions. And the first is the conceptual dimension, where we have here 6 examples. I mean, there are more. This is not a complete list, but important difference I have just shown is the difference between rate-based and event-based modeling. Then we have continuous time or discrete time, continuous valued or discrete valued. For example, you can build the AI version with vector matrix multiplication in an analog or digital fashion. In the digital fashion, you have discrete valued system, and in the analog, you have a continuous valued system. Then you have the difference between exact computations and approximate or noisy or stochastic computations. You heard from Brad that stochastic might be very important. And you see already here, this is not a simple either or. It is very the full range of alternatives to the exact version. And also the exact is not simple because it can be exact with 8 bits or with 12 bits, with floats, with p floats. So it's also, it can analytical precise mathematical description. So it's not that simple. Then we have point neurons or structured neurons. We have heard in biology, structured neurons are important. We have linear dendrites or nonlinear dendrites, so we can have just a passive summation, or we can have action potentials in the dendrites. And also the system can be static, so we have a snapshot of a network and just operate it, like, for example, if you use the network just for inference, or we can have a plastic system that changes during operation. Either in a positive sense, we are learning, but it can also deteriorate, like a memristor-based system will deteriorate during operation, for example. So these are the conceptual dimensions, but we do not do this only in simulation. We want to implement these systems. So we have also technological dimensions. And this is even more, has even a higher variety. We have analog digital. This is the main, maybe difference also in EBRAINS. It's between Spinnaker and BrainScaleS. But also we have, for example, analog electrical or optical implementation. We will hear optical implementations of neural networks later in the conference. Then we can have standard CMOS, like in the BrainScaleS case, or novel devices. It can be fully programmable or fixed. It can be in-memory computing or phenomenon computing. It can have constant speed. That means continuous time or kind of a real-time implementation. This real-time can be biological real-time or accelerated or even slowed down. That's also possible, but I've never heard of an example here. And it can also be a variable speed. That means best effort. For example, Loihi does it. If it has to calculate a lot, the time stretches. If it has not calculated so much, time is compressed. And last but not least, the systems are going to be used, and so there's an application dimension. And here the biggest or the most important dimension is research or commercial, because these are very different requirements. BrainScaleS is mostly for research, but not 100%. Then is the target brain emulation, or is the target machine learning or AI? This is also one of the basic differences in application. Then also the important constraints like energy, size, and cost. I mean, is it constrained or not constrained? This is very important for the design considerations you have to make. And then is it a fixed system for, let's say, one product and will never change, or is it a system that needs to adapt because, for example, the data changes over time or so? So this is a very condensed summary of the whole range of neuromorphic solutions. And BrainScaleS, just to remind you, since we have had BrainScaleS talks every year, I didn't want to repeat an introduction in BrainScaleS this year. So just a very short summary. You have an analog CMOS-based system based on BrainScaleS chips, and they contain a lot of synapses and some neurons. And in principle, they integrate on the analog membrane capacitance, the input signals of the synapses. And then they have special circuits mimicking ion channels for exponential behavior, adaptation, and also for the spike generation. And these neuron circuits, they are modular. You can combine them to build the structure of a distributed neuron, and also use this then to have different kind of active dendrites, like, for example, calcium spikes here in the apical dendrite. To emulate these. And all these analog circuits have parameters to try to match them to some biological examples you want to emulate. So if we go back to the dimensions, BrainScaleS basically covers the analog continuous spike-based part of the concept, but with the structured neurons and nonlinear dendrites and plasticity. In the technological area, it's all to the left because I arranged it this way. It's analog electrical standard CMOS system. And for the applications, it's mostly for research. Brain emulation is the application in EBRAINS. And it is for, the idea is to emulate, have energy constrained systems so that it is more energy efficient than other solutions, but that is not the main target. But this is also not so simple, because these are only the primary aspects of the system. If you look closer, you see that also the green ones are valid. For example, it can also emulate rate-based systems. You have processors in it that do exact computations, so part of the computations are also exact. Then if you can do structured neurons, you usually can also do point neurons. You can do the simpler version. You can do linear dendrites, and you can also switch off plasticity, and then you have a static system. Also, parts of the systems are digital, so it's not that easy. And so parts do also calculate in von Neumann computing way and with the best effort concerning speed. So this is just to show that this kind of systems have a very broad range of applications. And so for EBRAINS, we need to cover a lot of subcategories for the EBRAINS services to make this, because there are different application dimensions, mean we have different, use different parts of the technological dimensions and cover different conceptual dimensions. Here's a summary of subcategories we will offer in EBRAINS. So EBRAINS is basically a kind of a software environment that what the user sees at the first place. Behind that are the services, and the idea is that for the different kind of target applications, the BrainScaleS services will have the necessary software to make the system easily accessible for the user. I won't go through this here in detail, just to highlight a few things, because we've already mentioned in the conference, the accelerated emulation of networks of structured neurons with nonlinear dendrites. This was at the very beginning in the opinions round that this is an important aspect for brain emulation, and I also think this is the most important aspect to understand the brain. We have to emulate structured neurons. Another thing, we heard about structural plasticity, and we heard that Spinnaker covers structural plasticity. And just to add here that obviously BrainScaleS also covers structural plasticity on a local synaptic level. And here's a according publication if you're interested in it. And also, it's not all about biology. For example, for the application dimension, in the industrial application dimension, it's interesting to have a really low energy information processing based on spike-based system, where you have very sparse systems that you can train, for example, for voice recognition to have very low energy solutions. And this can also be done with BrainScaleS and in the EBRAINS framework. And for example, here the inference experiments for solving tasks using optimized networks parameters generated by hardware in the loop gradient-based training. That long sentence means you can train a spike-based network in the same way you train a classical deep neural network, but the values are represented by the spike times, and this gives you, and you can optimize for low latency and sparse spikes, and this gives you the optimal energy efficiency and very low latency in this accelerated framework. In our case, it's only a few microseconds. And all this, and then this services will be available in EBRAINS when it's up and running. This will be in the next year or so, but a subset of these are already accessible. And in the online demos, which we have this evening and had yesterday, you can try out a few of these. And I think you can still register for today's hands-on if you are interested. One last service I want to show, because here I will also present an example. It's a novel thing we have only started recently. That's a parameter fitting to match experimental observations. And here the task is that in biology you do not have Hodgkin-Huxley equation with all parameters known, but you have just some measurements from a wet lab or an in vivo animal, mostly maybe just some membrane, some membrane potentials and some spike times. And then you want to fit your neuromorphic circuit to model this neuron you have in the experiments. And here we are working with a model, with a method from Pedro Gonçalves et al. Training deep neural density estimators to identify mechanistic models of neural dynamics. And it works in principle by training a neural density estimator, which learns what are the best parameters that, for your model to match the experimental data. And the interesting thing here is that the mechanistic model and the simulated data, they can be replaced easily by the hardware model and the measured data from the hardware system. So you get as a posterior distribution the probability that some parameters you load on the hardware will make the hardware emulate your data from your experiments as best, in the best possible way. And here are some early results from this research. They are done by Jakob Kaiser, a PhD, in collaboration with Sebastian Schmidt von Göttingen. And here we have a chain of 5 dendritic compartments and 2 parameters. One is for the actual conductance, that means the conductance between the compartments, and one is for the leakage in the individual compartments. And here we have only 2 parameters, so all compartments have the same parameters and they are not calibrated. So we have the fixed pattern noise of the analog hardware and so on. And in this case here, the reference measurement, so you insert a pulse here and you see in each compartment it gets weaker. It's the blue point, and then you see that the best parameter, if you then from the parameter field here, you just take some examples, you see these darker black ones match much better the target than the lighter ones. And this is from one chip, so you can argue maybe if you use the same chip as an example, that is not what you will have later, but you can also use a different chip. This is more like having a measurement and then trying to match the model to it. And you see that now you cannot fit it 100%. You would need more parameters to fit it 100%, but you can fit it still reliably. The points here that the neural network predicts are much better than randomly chosen parameter combinations. So we will work on this scheme to extend it to more parameters and more complex models to really be able to match biological neuron islets under investigation in the lab, and then help the experimenter to guide him through his experimental paradigm using the modeled system, maybe in more complex context. For example, you can put the matched neuron in a larger network in the chip to make some predictions, and then compare the predictions to what you measure in the biological example. So to summarize, easily accessible analog computing, this is the goal of EBRAINS neuromorphic service BrainScaleS. And this means we make conceptual neuromorphic dimensions of BrainScaleS remote accessible through this EBRAINS service. Therefore, we have to encapsulate the technological neuromorphic dimensions into the EBRAINS remote user framework. This is a lot of software. I have not talked about any details because the expert Eric Müller will explain everything to you in the hands-on sessions. And by this, we can support all the application dimensions I have shown so far. And also, this is my invention, there's EBRAINS dimensions. And this means the software we need to do this, the user interface, the documentation, the tutorials, support for the users, and the hardware operation and maintenance. So this EBRAINS dimensions is what we have to do in our lab to maintain this service for the users, and what we hopefully will be able to do then in the future in EBRAINS. So thank you.